So, we are going to start here into Unit 3 today. A lot more with polynomials. It does get us away from some of the graphing things, but not everything. So, to put some of you a little more at ease here when you're looking up at the top and going, what the freak is that? Okay. Basically, what I'm doing is we're going to be paying attention to the stuff over in this left-hand area a little bit more. We're going to pay more attention to degree, and as we start to work with more of these, we'll start to understand what some of these look more like. Like, for instance, we don't see constant terms graphed. Like, constant is something that's just like a number, like 5 or something like that. So, again, we don't see those graphed very often. Linear, we do see those. That's something where you have something like y equals x plus 6. It's a line, hence linear, okay? So that's one we'll get a lot of experience with. Quadratics, we just got done with. That's when I have something to the squared power. That's when the parabolas show up. Cubics, now we've heard of cubics. We've dealt with some cubics. We haven't really graphed them yet, though. Yeah, kind of like Rubik's Cube. But that would be something to the third. That's going to be making what's called a hyperbola. Now, again, that's not important right now. It's just a little bit of heads-up information.
Oh, that's...
And the last two, we never actually get into graphing in here. We'll look at some pictures, but it's not like you're going to have to figure out how to graph them. So if something is of degree 4, if the exponent, the largest exponent we see is a 4, that's called a quartic polynomial. And if it was a fifth, it was a quintic. And I guess they got bored coming up with names because anything after 5, they just call it a polynomial of degree whatever. So you're like, okay, what's that have to do with me? Well, let me tell you what that has to do with you. We have this little chart down here below. And before we get into it, the first question here says, decide whether the function is a polynomial. Well, I was nice. I made these all polynomial functions. So you're like, well, how am I going to know when I see one that isn't then? One of two things basically is going to happen. We're going to write those down here, and you're probably going to run into them sometime with the homework here. All right, so one time that it would not be a polynomial would be if you have x in the denominator of a fraction. You're like, well, why is that a big deal? Well, if you think about it, when we've had x's in the denominators, what that typically means is that you're dealing with a negative exponent. Negative exponents never will pass our test for figuring out if something's a function or not. It won't be able to pass the vertical line test. So that's one thing I can look out for. So if I ever see something that says like x over 4, nope, not a function. X to the negative third, nope, not a function. And the other one would be if I have a variable exponent. So like if you had y equals 2 to the x power, nope, not going to work. We might be looking at a picture at that one a little later today, but if not, it'll be coming soon. But those are basically the two situations I can run into that are going to cause me a problem. And if we run into some others as we go, we'll add them in. But those are the two ones that occur most often. So when we get down to this chart, it says decide whether it's a polynomial. They're all going to be. I gave that away. If it is, write the function in standard form. All standard form means is we go from the biggest exponent term down to the smallest one. So if I look at this, which one of my terms has the largest exponent? Where do you see the biggest exponent? Yeah, negative 3x to the 4th. Wherever I see the largest exponent, I'm going to write that term down first.
And it was then like 1/2 at x squared.
Yeah.
And then negative 7.
Right, because I'm going from the greatest exponent, or in this case, the greatest degree to the least.
Least.
Yeah. So 4 down to 2, and anytime I get a constant term, that's like having a degree of 0. That's always going to be at the end if we have a plain old number. So once it's in standard form, then we go and we go, okay, well, the degree. The degree is the largest exponent.
So that's 4.
So it means a degree of 4. And normally what that also is going to tell us for future reference is how many solutions there are, how many zeros there are. But that's for another time. Type, we're just kind of getting used to some of the language here a little bit. So something of degree 4 is called a quartic function. No, that is not something you're going to have memorized. Okay, no worries there. And then my lead coefficient, once I'm in standard form, is just the coefficient at the start of the problem. In this case, it's -3. You notice how I could get into trouble, though, if I didn't have it in standard form. If I didn't have it in standard form, I'd probably write down 1/2 the lead coefficient, and that wouldn't be right. So sometimes we may have to rearrange these. Other times, 3, 2. That's already in the right order. Okay. That makes life simple. Let's see here. What's my degree going to be this time? 3, because it's the biggest exponent. The exponents of 3 are going to give me cubics. And what's my lead coefficient going to be this time?
2.
2. Because that's what's out front. You're like, okay, this isn't terrible. So I'm just going from the greatest exponent down to whatever the least is. And then basically once I get there, everything else I need is in that very first term, and that would be true.
Yeah.
I find my degree in that term. Yep. I find that lead coefficient there. And I figure out the type from there too. But it's all about being in standard form. Now don't let number 4, the fact that I'm throwing weird things like radicals and pi and that stuff in there, mess you up. Keep doing the same thing. Biggest exponent, first term. Next biggest.
-0.5.
Yep, next term in my constants are...
Square root 2.
That's right.
So if it would be a square root or anything, you just have it act like it's regular 2.
Yeah, it's still going to be a constant since it's still just a number. And then I still am just going to take my degree from the first term. My type, and then my lead coefficient. Yes, it can even be funky symbol numbers like pi. But again, this unit's more about just getting used to some of the language like degree and lead coefficient and things like that more than anything else.
Have something that's foreign be common.
Right, that's what we're going to shoot for, because when we get to the part on the back here, I keep comparing it to a foreign language. So we'll see how this works out for us. So one way, if I want to find out a specific part of a polynomial, a specific value, is to use substitution. Now you've been doing this for a long time. Like for instance, f of x, just a reminder, f of x and y are the same thing. Okay? The reason we use f of x is, then if I'm looking for a specific value, like let's say I want to know what this function's value is at 3. I plug in the 3 here, and you notice everywhere that there was an x, I plug in a 3. You're like, well, this is just like regular substitution's always been. And if I were to type that in my calculator, I'd get 98 out.
Equals
and that's what my f of 3 is going to be. So now, f of 3, just to make myself clear, okay, that's just a label. That's not part of the problem. So when I'm looking at f of 3, f of whatever, that's just a label. It's not like you need to divide by 3 to figure out what f is. That's just telling me if the x value is at 3, then the y value, f of x, is going to be 98. So when I go to evaluate a function, I'm basically just saying substitute the x value in and tell me what the answer is going to be. You're like, well, shoot, I've been doing this forever. So here, I'm going to plug in the -4 where the x goes.
So it's just basically just distributions.
Yeah, I'm just going to multiply these. So 3 times -4 is -12. Minus 5 is -17. And that would be my f of -4. It's f of and whatever I plugged in for x.
So no solving.
No solving for f. It's just a label. And so basically on any of these, what I'm going to be doing is, again, I'm plugging that x value in. So I'm like, okay, 1 minus 2 is negative 1. Now, what's absolute value do to whatever number comes out of it?
1.
Yeah, it's going to make it positive. So this is going to become 1, and I get my answer. So really nothing different here than with substitution. However, I do want to show you one other way you could do this. Now, some of you are going to continue to feel comfortable, and that's fine, taking a problem like this and just saying, okay, I'm going to put my negative 2 in everywhere that I see x. Now, some of you have issues with not remembering the parentheses, or forgetting a sign, or something like that. If that describes you at all sometimes, I have a plan. And it's going to let us use a function on the calculator to help us out with these things if they tend to get us in a little bit of trouble. And it's called the store function. So here's how the store function works. If I know what my x value that I'm going to plug in is, I type that number in, and then I hit the store button. It's right above on here, this STO with an arrow. And when I hit that, this little arrow comes up. Now, it's not the cool part yet. And then I'm going to hit X, because that's what I wanted to plug in for X. I'm going to hit Enter. You're like, well, is the answer negative 2? No. That's the calculator telling me, okay, so you want me to plug a negative 2 in every time whatever you type in next is. And I'm like, yes. So I'm going to take what I have here. I'm not going to y equals. I'm just going to type it right here. Exactly like what I see there. I'm not changing the x's because the calculator knows what it's going to plug in. Hit enter. That's the answer. So in this case, g of negative 2, because that's what I plugged in for x, equals 11. Now, if you wanted to do it old school, like we've been doing, that's fine. I just like showing you options for things. If you tend to make those kind of careless mistakes sometimes, so I just did the exact same thing, I just did it without the substitution, just to show you that I got the same answer either way.
With the store on there.
Yeah. Store I can use for any problem where I'm substituting a value in. But again, as you noticed here, it's not like it saved me 5 minutes doing it one way versus the other. It's just one of those things that I can maybe use to double check if I need to. But it's not something that if you're like, yeah, I really don't think I'm going to use that you have to or else. I won't say on a question on a quiz, use the store function. Don't do that to you. I promise I won't do it.
Yeah, I probably won't remember how to do the store function anyway.
That could be it too.
And I won't even know how to do it to begin with. You know how to do it to begin with.
Right. So okay, now here's the one where we've got to relax. This is our foreign language part of the lesson. We're going to talk about the end behavior of graphs. Now you're like, well, what do you mean the end behavior?
Yeah.
When I look at the arrows at the two ends of my graphs, what directions are they going? That's basically what I'm going to be trying to communicate here. But here's something I'm going to have you jot down just so you can understand how this works, because this language in here can get a little bit tricky. So here's how I want you to think about this. This, okay, if I were to say this in English, is the way I like to put it, this says x is approaching negative infinity. You're like, okay, what exactly does that mean? Sounds like a foreign language. In English, this means as x goes left. Because if you think about a number line, if you would think about, if I were to sit here and draw a number line like we've had before, we always talk about if it goes forever off to the left, it's going off to negative infinity. And that's what we're doing now. We're saying if x approaches negative infinity, if we're going to the left, okay, and if it's positive infinity down there, you'll never guess. As x goes to the right. And I want you to think about it this way first. So as x goes to the right, we're approaching positive infinity. Now, when we start to do these, we're just going to talk about left, right, up, down. We'll get all this fancy infinity speak in later. Just like when you're doing a foreign language, we don't throw you right into the 4th year and we're talking all in Spanish. We actually learn the words first. So then you're like, okay, so what do we do for y then? Well, let me tell you what we're going to do for y. When we get to y, and I'm going to kind of move this around a little bit. I'll try to pause this for a second. What we're going to do now, because remember, f of x is the same thing as saying y, okay? So when I see f of x is approaching, let's say, negative infinity, let's think about this for a minute. If you're thinking about directions, what direction am I going with y when I'm approaching negative infinity?
Down.
Down. So this is just saying as y goes down. And like I said, we're just going to talk in x, y, up, down directions first. We'll get into the fancy language later. And then if we've got f of x approaches infinity, well, if f of x, if my y is approaching positive infinity, we're going up. So what I basically am going to be doing in here, when I put these all together, is saying what happens to y when x goes left? What happens to y when x goes right? And we're just going to make kind of a mathematical sentence out of it, is what's going to happen here. So what we're going to do, move this out of the way for now. I might have to put that back in here in a minute. So, like it says here, basically we're describing what happens to the function as it travels to the left and then to the right. So, everything goes better when you have a picture. So what we're going to do is we are going to look at a picture of each of these particular functions. So let me get that out of here. Remember, f of x is a fancy way of saying y. So I'm just going to type in the other side. So y equals 4x, graph. You're like, Harty, big deal. It's a line. Okay, but let's think about that for a minute. I don't have to draw my line perfectly. Okay, there's my line. Now let's bring back what we were just talking about for a second here. Okay, so if this is where x approaches negative infinity, and here's where it approaches positive as I go to the right, and up here, this is my f of x, or I can call it y, approaches positive infinity. And this is where it approaches negative. And again, I just want you to be able to visually see what's going on. Here's my job. I need to put into words what's going on here. So here's how this is going to work each time. We're going to make a sentence out of this. And I'm going to finish the end of my sentence first. So I'm going to write as x goes left, just like this first one was here. And right below it, I'm going to have as x goes right. Now just stay with me for a second. I've got to finish the first part of the sentence on each one. And then we're going to turn it into math lingo. So as I'm on this line, this straight line right here, as my x value goes to the left, as I start to move left on this line, what direction am I heading in the y value? Am I going up or down? I'm going down. So what I'm going to do is I'm going to write on here as y goes down. As x is going left, y is going down. I'm just verbally describing what's happening to the line. So then I do it for the other part. Okay, when x goes right, so I'm on that same line and I'm heading to the right.
And you're going up.
I'm going up now for my y. So y goes up as x goes right. this, what you're describing right here in words, that's what end behavior is. You're describing what's happening at the end of the graph. Now comes the fun part. Now we get to turn it into the foreign language. And we're going to kind of use what we wrote up here as our guide.
So basically, I mean, just graph it as it is. Basically, just graph the problem as it is, and then do it. Basically.
Then we're trying to figure out where it goes once we see it. So as y goes down, I'm just going to copy what this says. So f of x approaches negative infinity, because that's our way of translating as y goes down. X goes left. Okay. As x approaches negative infinity. So this is our foreign way of saying as y goes down, x goes left. Just translation, like if you put it in Google Translate or something. And then the bottom one says y goes up. Okay, so when y goes up, it's f of x approaches infinity. As x goes right. Okay. As x approaches infinity. This is our mathematical way of saying what we said in English right above, for us to be able to describe what's going on without just writing it out in words. We always are using infinity and negative infinity for everything. Even if some of you for now need to replace f of x with y because that confuses you, that's okay. We'll get you to a point that you're kind of seeing how this works. But it's like anything else. The first time you heard a foreign language, you're probably like, I'm never going to get under this. I understand uno, dos, and tres, and that's about it. Well, that might be where you're at with this right now. But it won't be forever. Because we're going to keep playing with these. We're going to say, okay, let's look at another picture. Negative 4x squared. Graph. Ooh.
Sorry.
So we've got a parabola that's opening down. Now again, it doesn't have to be perfect. So I look and I say, okay, what do I notice about all of my directions here? Well, let's see. I need to know what y does as x goes left, and I need to know what y does as x goes right. And I can always deal with all the funky language stuff later. So if I start here and I start moving to the left on the graph, what direction y are we going in? Down. So y goes down as x goes left. Okay, that makes sense. So then I start up here again. I'm like, okay, well, what happens if I go right, though? If I go right, what's happening to y? It's still going down. So once I've put it in English, in my own language, now I'm going to put it in the mathematical language. And again, if I've got a peek at these for right now until I get used to it more, that's okay. So get this out of the way. So okay, so y goes down. F of x approaches negative infinity as x goes left. When I go left, I go to negative infinity. When I go down, I go to negative infinity. And that's all we're really doing here. As y goes down, okay, so it's negative infinity again, because down is negative. As x goes right, and when I go to the right, I get positive infinity numbers. And I've got my end behavior. And like I said, as you get used to it more, you might not have to write down the down, left, down, right, and then do this. You might be able to go straight to this. That'd be great. That's what we're shooting for. But if it takes doing some of these before I get there, not the worst thing that ever happened. So one more in this section. Let's see here. Negative x to the third 5x minus 1. Make sure I typed that in right. Looks good. That's kind of funky. That's a hyperbola. We'll be getting to some of those. So I'll get my hyperbola drawn in here. And again, I'm just looking for a sketch because I'm trying to see where those arrows are going. All right. X goes left. X goes right. That's always part of what we're going to do. So then I start looking, what's the y value doing as each of those things occur? So as my graph's going to the left here, what's happening to y? Going up this time. Y goes up. Now some of you may be looking and saying, well, wait a minute though. If I start here, it's going down. But think about it, near the arrows is where we're looking, because that's where it's heading off to. So I want to be in the arrow area. What about when x is going to the right? Down we go. Y goes down. So there's my English. Now I got to translate. F of x approaches. When y goes up, that's positive infinity. As x, when with our x's we go to the left, that's negative infinity. I'm like, okay. Then my next sentence here, y goes down, negative infinity, as x goes right, positive infinity. This is what I'm looking for. And again, if it takes a few to get to the fancy language, that's okay. The only other thing we're going to be doing with these is going to be figuring out domain and range. Now, when it comes to domain and range, I'll admit it, I have to be a little more specific. So specific that I have to have one of these? Not necessarily. I've seen apps for phones with graphing calculators that give you a very accurate picture. You've got the one on the computer that can be downloaded, or if you happen to have a graphing calculator, that's fine. But it's not one of those things where, oh, I don't have one of yours, I can't do this. Yeah, you actually can. So, okay. Now I graph this one. I'm like, okay, but you just said I need to be a little more specific. We do. This is one of those where I'm hoping, and if you don't, that's okay. I want to find where that vertex is going to be. Now, it looks like it's at 3. If I want to look at the chart, I can look. Okay, it is. How do I know that? 3 is the lowest value. If it's opening up and I'm finding a min, I'm going to find where that lowest value is. And since I already have this chart up, I'm just going to go ahead and plot a few extra points so I can make it look nice. So I get my sketch in. I say, okay. Oh, domain and range, it's been a while. It's been a little while. Remember, domain is my x values. Range is my y. I'm always doing least to greatest. Nice thing about domain, if you see arrows on both sides of your graph, oh, I do, that's going to be negative infinity to infinity every time because they're going to keep going forever to the left and right. Range, though, I have to think a little bit more because this doesn't look like it goes up forever. I see that positive infinity part, but it doesn't go down forever. How far down does it go? To 3. There's my range. Okay, it's always least to greatest. So in this case, it's bottom to top on my range. And I'll admit, some of these graphs that we're going to take a peek at look really weird. You're like, where'd that come from?
How weird?
Well, let's see how weird we can get. Oops. Gotta get
That would have been good.
+1. Okay, I got, yeah.
Would it be like easier for like if you're going like square on a graph, but you just square then go back and like overwrite the number on there? And, like,
You could. Yep, you could. Now, this one kind of looks weird. It looks like a lopsided parabola. So here's my biggest concern here. I want that smallest x value. So let's see.
0.
Looks like it's 0. So I see -1, 0, I see a point. That's a big deal to me to get. The other ones, well, I'll plot a few again because.
But why 0, not the smallest x value?
Because when I remember with my domain, my x values, I'm going to have negative infinity to infinity. It's not going to matter. With my range, though, I need to know how low it goes. So by knowing where the smallest y value is, that's going to help me find out where my range starts.
Oh, so it's the negative. So it's the -1, but not at 0.
Right. So I'm going to be looking here when I actually plot these points and get this funky looking graph. I still have the 2 arrows, so my domain is still going to be the same. But my range is a little different now. Because again, it goes up forever, so I have positive infinity. But now I know where that lowest point's at, where that minimum is. It's at y equals 0. And that's why I wanted to find that lowest y when I'm doing these. Because that's going to be helpful when I'm looking for my range. But occasionally, and I saved the easiest one for last. Oh, and then I cleared it all out.
Oh.
So, sometimes you're going to get situations where maybe you get arrows going both directions.
What?
So like here, if I'm sketching, you're like, now why are you not worrying about the table this time, Harty? Because I saw something that I like. I see arrows going in both directions. Oh, happy. Because when that happens, it's still going to keep going to the right forever and to the left forever, my domain, but it's also going to keep going up and down forever. If I get arrows going in both directions, that's the easiest domain and range ever. Because I just get those set that way. So here's our game plan. At least this would be my game plan with about, 15 minutes almost to play with here, 10, 15. My plan on the worksheet would be this. Is it pops up here.
Oh, that's...
Okay, for those first 10 questions, you're going to do the degree and the lead coefficient. You don't need a calculator or anything fancy for that. But identify the end behavior. Uh-oh, I need a picture. I would type in these expressions into the calculator and just sketch the graphs. So later, when I'm trying to figure out the end behavior, I have pictures of all of them. Because anything that's just plain old math, you can do with any calculator at any time. Doesn't matter. But if you're identifying end behavior or domain and range, I would sketch pictures now. So you don't have to wait till later on this. Okay?
Okay, that's the lowest y value.
Yeah, but that's only when you're doing domain and range. So like
no.
on the worksheet, until you get to number 11, you don't have to do domain and range.
Oh, so is